Hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering. I'm here to present you the subject non-destructive evaluation and testing, subject code ME419. We are discussing unit number 2, lecture number 14 in the series. Today's topic are radiographic interpretation. In this, weldings and casting defects will be discussed, radiation detectors and safety control will be discussed. So our learning objective for today is to provide the students with a basic understanding of radiographic interpretation for welds and castings, to know about radiation detectors and safety controls. Our outcome will be students will have an understanding of radiographic interpretation for welds and casting, and student will understand various factors influencing radiation detectors and safety control. So outcomes are really important. So radiographic interpretation for welds. In addition to producing high quality radiographs, the radiographer must also be skilled in radiographic interpretation. Interpretation of radiographs takes place in three basic steps. First, detection. Second, interpretation. Third, evaluation. All of these steps make use of the radiographer's visual activity. Visual activity is the ability to resolve a spatial pattern in an image. The ability of an individual to detect discontinuities in radiography is also affected by the lighting condition in the place of viewing and the experience level for recognizing various features in the image. We also know that the inspector should have a proper lighting condition in the place of viewing. The inspector should have experience for recognizing various features in the image. The following material was developed to help students develop understanding of all types of defects found in weldments and how they appear in the radiograph. So, these discontinuities. Now, discontinuities are interruptions in the typical structure of a material. These interruptions may occur in the base metal, weld material, or heat affected zone. While welding, the uh, material on which we are welding is called a base metal. The material through which we are welding it is called a weld material, and the zone where the fusion actually happens is called the heat affected zone. So discontinuities which do not meet the requirement of the codes or specification used to invoke and control inspection are referred to as defects. So the following discontinuities are typical of all types of welding. The first one is the cold lap. In the cold lab, what happens? It is a condition where the weld filler metal does not properly fuse with the base metal or the previous weld pass material interpass cold lab. What happens during the welding process? There is a filler metal, okay, which has to properly fuse with the base metal for proper welding. But if the filler metal is not able to properly fuse with the base metal, then there will be a discontinuity called as cold lap. Okay, the arc does not melt the base metal sufficiently and causes the slightly molten puddle to flow into the base material without bonding. So if the bonding is not proper, the welding will not be proper. This is called as a cold lap. You can see in this diagram also how the cold lab radiographic interpretation is seen. In the upper figure, you can see on the left hand side, there is shown that how this cold lab, how the fusion has not always happened. And in the bottom figure, you can also see the mark showing the cold lab space. So this cold lab is a discontinuity which needs to be considered and is found to be a defect or a discontinuity in the welding, or you can say in the weldments. So this is a kind of radiographic interpretation known as cold lab, that is a defect in the weldments. Another is porosity. Okay, now porosity is the result of gas entrapped in the solidifying metal. Porosity can take many shapes on a radiograph, but often appears as dark, round, or irregular spots or specks appearing singularly in clusters or in rows. Okay, now sometimes porosity is elongated and may appear to have a tail. So this is the result of gas attempting to escape while the metal is still in a liquid state. and is called a wormhole porosity. What happens whenever there is a fusion taking place? At that time, some gases are involved. So when the gases involved are not able to escape, they result in gas entrapment, where in the solidifying metal zone only. Okay, at the fusion zone where the metals solidify, the gases are entrapped. So they just form a porosity kind of a defect in the welding zone only. Okay, so whenever you go on a radiograph, okay, they appear as dark round or irregular spots or specks. Okay, it may be in a single, you can say single spot, or it may be in clusters, or it may be in rows, depending upon the gas entrapped in the solidifying metal. Okay, so it can be also be seen as a tail. Okay, why? Because the gas is not able to escape. So all porosity is a void. Is it is an empty space in the material, and it will have a higher radiographic density than the surrounding area. When you will do the radiography, you will find that the density is shown at that point where the gas is entrapped. It will have a higher radiographic density than the surrounding nearby areas. So it is a kind of a void in the material. So porosity is a kind of a defect. Okay, it can be seen as an irregular spot. Okay, it can be seen as a dark round. Okay, it is the result of gas entrapped in the solidifying metal. Let me show you this with the help of a figure. You can see in this figure how this porosity as shown. You can see on the left hand side, on the upper side, there are small black dots appearing on the welding zone. In the bottom figure also you can see there are some spots appearing on this. But on the right hand side on the radiographic plane you can also see some kind of spots. These are all porosity. These are all entrapped gases. These are all voids due to porosity. Okay, so we should have proper experience to judge. Okay, this is the kind of a defect known as porosity. Okay, now let's go forward. Now cluster porosity. Now cluster porosity is caused when flux coated electrodes are contaminated with moisture. The moisture turns into a gas when heated and becomes trapped in a weld during the welding process. I repeat what happens in cluster porosity when it is caused when flux coated electrodes are contaminated with moisture. If there is moisture with the electrodes, what happens when the welding happens? This moisture it turns into a gas when heated. Okay, and when this gas is trapped at the welding zone during the welding process, so this becomes cluster porosity. It is just like a regular porosity. The cluster porosity appears just like regular porosity in the radiograph, but the indications will be grouped close together. Its indications are that it will be grouped close together. Okay, it is same as regular porosity, but it is the form of cluster. Okay, it is due to the moisture. Okay, na? So let's see the diagram. You can see the in the upper diagram on the left hand side. There is a cluster of dots, dark dots, spots on the diagram. This shows cluster porosity at the welding zone. Also in the bottom diagram, you can also see some dots are there. This is all you can say cluster zone. In the right hand side of the radiograph, you can see a cluster of you can say dark spots. So it is cluster porosity. Because if you compare with the simple porosity, wait, you can see here these dots are either singular or in cluster but less in number. This is showing simple cluster porosity, not simple porosity. Like a regular porosity, a gas is trapped. But if you compare it with the cluster porosity, okay, if you compare with the cluster porosity, see how many dots are trapped at one place. This is also gas entrapped at the welding zone, but this is cluster porosity. While if you compare with this regular porosity, so the inspector should be able to inspect that it is a cluster porosity or a simple porosity, a regular porosity defect. Both are considered a defect in this. Okay, both are a defect. You can see a discontinuity. Now slag's inclusions. The slag inclusions are non-metallic solid material. Slag inclusions are non-metallic solid material entrapped in the weld metal, or between weld and the base metal. Okay, it is like mm, you can say another material that is trapped between, you can say, weld metal and the base metal. Okay, so in a radiograph, dark, jagged, asymmetrical shape within the weld or along the weld zone areas are indicative of slag inclusion. I will show you this the figure. You can easily see that some kind of irregular shape is there. Okay, because this is not able to fuse properly with the you can say base metal and the filler metal. So it has remained inside the, you can say, welding zone. So during the weldment, it has not able to escape easily. So it has trapped in the welding zone during solidification process. So in the radiograph also you can see on the right hand side the irregular shapes are shown to you. These are slag inclusion, a kind of discontinuity. The discontinuity can weaken the strength of welding. So through radiography you can also you can say detect these kind of slag inclusions also, and avoid such slag inclusion if possible. Now, incomplete penetration or lack of penetration, called as IP or LOP, occurs when the weld metal fails to penetrate the joint. This occurs when the weld metal fails to penetrate the joint. It is one of the most objectionable weld discontinuities. Lack of penetration allows a natural stress riser from which a crack may propagate. Okay, see, this lack of penetration IP, it may lead to a crack. Okay, the appearance on a radiograph in a dark area with well defined straight edges that follows the land or the root face down the center of the weld. Okay, I'll show you this incomplete penetration or lack of penetration. Okay, let me show you this side. Now you can see that there is a lack of penetration in the above diagram. You can see that there is inadequate or lack of penetration of the welding material. So this is shown properly on the bottom figure. You can see the black line, a regular line. It is showing that there is a lack of penetration on this, inadequate penetration. Okay, so due to this incomplete penetration, you can also see on the radiograph interpretation on the right hand side. This interpretation will obviously show a black line which shows that the proper filling is not there. So you can say that this occurs when the weld metal fails to penetrate the joint, and this allows a natural stress riser. This allows a natural stress riser from which a crack may propagate. So this is not acceptable. This is kind of a defect or a discontinuity which can be interpreted with the help of radiographs also. Okay, let's go further. Now, radiographic interpretation for castings. Till now, we have studied about radiographic interpretations for welding. Now we are going with the casting process. Okay, your casting is also a process where defects happen due to some or the other reasons. So we will study for castings also, and these defects due to casting they can be interpreted with the help of radiographic interpretations. Okay, radiographic interpretation is also helpful in finding out the defects or discontinuities in castings also. The major objective of radiographic testing for castings is the disclosure of defects that adversely affect the strength of the product. So castings are a product form that often receive radiographic inspection, since many of the defects caused by the casting process are volumetric in nature and are thus relatively easy to detect with this method. Now these discontinuities are related to casting process deficiencies, obviously, because these are some kind of a defect, so this will lead to a deficiency. which, if properly understood, can lead to accurate accept or reject decisions as well as to suitable corrective measures. If you are able to find out the interpretation in a correct manner, then you can help in accepting or rejecting the workpiece to decide whether to accept or reject the workpiece. And if possible, suggest a suitable measure so that the casting cannot be rejected, it can be repaired or it can be, you can say, corrected if possible. Now, since different types and sizes of defects have different effects on the performance on the casting, it is important that a radiographer is able to identify the type and the size of the defect. So, if we are going for radiographic interpretation, if you're taking the, you can say, radiography, but the radiographer should able to identify, the inspector should able to identify the type and the size of defect. Only after that he will able to suggest some corrective measures or he can accept or reject it. So there are some standards of radiograph of casting. Okay, they are being produced like ASTM EI 155, ASTM EI 155, E1155. These are produced to help the radiographer to make a better assessment of the defects found in components. These are based upon the past experimentation, based upon the past results. They have created this document or database to help the radiographer for a better assessment of the defects found in components. Okay, these have all the details of the defects of the found in components. The castings that are used to produce the standard radiograph has been destructively analyzed to confirm the size and type of discontinuities present. So this database, it is helping the radiographer to make a better assessment of the defects found in components, which is really good, which is really good. Okay, which is making the work faster. So the most common discontinuities types that are seen or that have been included in the existing reference radiograph document. The first one is the gas porosity or blowholes. Okay. Now this is caused by accumulated gas or air which is trapped by the metal. What happens that when we are casting, somewhat what happens when the molten metal it comes in contact with the surface of the die casting or the sand. What happens at due to the difference in temperature or the material, some gases are they come, and if the gases are not able to escape easily, then they get accumulated or trapped inside the casting only. So these they lead to a discontinuity. Okay, these are voids inside this. So it is called as a gas porosity or blowholes. Now, these discontinuities are smooth walled rounded cavities of a spherical, elongated or flattened shape. They have this kind of different shapes. If the screw is not high enough to provide the necessary heat transfer needed to force the gas or air out of the mold, the gas or air will be trapped as the molten metal begins to solidify. The screw from where the gases escape inside the casting, inside you can say inside the whole this casting arrangement, the gases are not able to escape easily. Then what happens that the gases or the air that has been trapped during that has been increased during the casting process, sorry, in the casting process, they will be trapped when as the molten metal begins to solidify. So blows can be caused by sand that is too fine, too wet, or by sand that has low permeability, so that gas cannot escape. Now, blowholes they can be caused if the sand is too fine, or it is too wet, it has too much moisture in it, or by sand that has low permeability, so that the gases cannot escape. Too high a moisture content in the sand makes it difficult to carry the excessive volumes of water vapor away from the casting. Another cause of blows can be attributed to using green ladles, rusty or lamp chills and chaplets. Now, sand inclusions and draws. These are also radiographic interpretations for castings. These are non-metallic oxides which appear on the radiograph as irregular dark blotches. Okay, they come from disintegrated portions of mold or core walls or from the oxides formed in the melt, which are not being skimmed off prior to the introduction into the metal into the mold. So for this we can do the careful control of the melt, proper holding time in the ladle, and the skimming of the melt during pouring will minimize or obviate this source of trouble. So in this way, you can avoid this non-metallic oxides, okay, and avoid this irregular and dark blotches. So shrinkage. Shrinkage is a kind of a discontinuity that appears as dark spots on a radiograph. Shrinkage assumes various forms, but in all cases it occurs because the molten metal shrinks as it solidifies in all portions of the final casting. So you can see these are the some kind of dark spots on the radiograph. So how is it avoided? Now shrinkage is avoided by making sure that the volume of the casting is adequately fed by risers, which sacrificially retain the shrinkage. Okay, shrinkage in its various forms can be recognized by a number of characteristics on the radiograph. So normally we usually have four types of shrinkages that we normally see. Okay, now how what is this? A cavity or dendritic or filamentary or sponge type? Okay, so they appear as dark spots on the radiograph. Okay, so how do we discuss that? Now, see, cavity shrinkage, they appears as areas with distinct jagged boundaries. You can see them, the jagged boundaries. It may produce when metal solidifies between two original streams of metal coming from opposite sides to form a common front. So this may lead to cavity shrinkage. Okay, so cavity shrinkage usually occurs at a time when the melt has almost reached a solidification temperature. The temperature at which solidification will start, and there is no source of supplementary liquid to feed possible cavities. Okay, you cannot supply you cannot there is no source of supplementary liquids to feed possible cavities the empty specimen side. So this may lead to cavity shrinkage. Now, dendritic shrinkage, it is a distribution of very fine lines or small elongated cavities that may vary in density and are usually unconnected. Okay. Now, filamentary shrinkage, they usually occurs as a continuous structure of connected lines or branches of variable length, width, and density, or occasionally as a network. So these three are a kind of a shrinkage discontinuity. Okay. Then commuted tomography. Computed tomography, say it is a kind of also NDT, non-destructive evaluation technique for 2D and 3D cross-sectional images of an object from flat axes. Okay, there the characteristics of internal structures of an object like dimension, shape, internal defects, and density. These are easily readily available from these computed tomography images. What we do in this is we do that the test component is placed on a turnable stage. Okay, that is between the radiation source and an imaging system. I'll show you with the help of this diagram. You can see this component. It is between the X-ray tube and the image intensifier. And then you have all the arrangement of like PC with image capturing hardware and all serial links to enable interference things. So you can see that you can see on the table on which it is tell it is computer controlled turntable. On which the test component is kept. No, it is computer controlled turntable. So what happens in this? Mhm. Oh, sorry. The test component is placed on a turnable stage that is between a radiation source and an imaging system. The turntable and the imaging system are connected to a computer so that the X-rays images collected can be correlated to the position of the test component. So the imaging system produces a two-dimensional shadowgraph image of the specimen, just like a film radiograph. This is a kind of a technology that is being used somewhere to find out the you can say 2D and 3D cross-sectional images of an object from flat X-ray. Advantage is that it has the it can be used to inspect both internal and defects, surface defects. It has ability to inspect parts covered for hidden by other parts of structure. Minimum part preparation required. Permanent test records are obtained. Both surface and internal responsibilities can be detected. And the disadvantage is like it is most expensive, and you can say area must be cleared of other personnel to avoid extra exposure. Test method is highly directional, depends on crack or extra source orientation, obviously, because that is important. Then high degree of skill required for very technique development and radiographic interpretation. Defects such as crack perpendicular to the radiation cannot cracks differ. Defects such as crack perpendicular to the radiation beam cannot be detected by radiographic testing. So radiography is readily used on flat plates. Now the application. The radiographic testing can be used on all metals to detect defects with an appreciable dimensions parallel to the radiation being or below the surface of the object. Radiographic testing is most applicable on three-dimensional defects, but dependent on radiation energy. Radiographic testing can be used on material thickness up to 10, 100, sorry, up to 100 or more. Now there are some radiation detectors that we are need to discuss. Okay. Now instrument used for radiation measurement, they fall into two broad categories like rate measuring instruments or personal dose measuring instruments. Now rate measuring instruments means those are those instruments that measure the rate at which the exposure is received, commonly called as the radiation intensity. There are several kinds of you can say rate measuring instruments like survey meters, audible alarms, area monitors that fall into this category. Okay, so we're discussing all about them. So dose measuring instruments, these are those instruments that measure the total amount of exposure received during the measuring period, like the dose measuring instruments or dosimeters, you can call them as dosimeters that are commonly used in industrial radiography are small devices which are designed to be worn by an individual to measure the exposure received by the individual. So an analogy can be made between these instruments and an odometer of a car because both are measuring accumulated units. Now survey meters. Now we are starting with this. Now the survey meter, as you can see in the diagram, it is also the important instrument. So what does it is the most important resource that a radiographer uses to determine the presence and intensity of a radiation. So it is used to determine the presence and intensity of a radiation. Okay, these are different. There are different models of survey meter that are available to measure radiation in the field. So they basically consist of a detector, as the name says, survey meter. So they will have a detector and a readout display. Okay, and in this both analog and digital display are available for proper, you can say, seeing. The most of the survey meters are used for industrial radiography. We use a gas field detector in this. Though, so last this was about gas filled detectors. Now these consist of a gas filled cylinder with two electrodes having a voltage applied to them. So whenever the device is brought near radioactive substances, the gas become ionized. Okay. Now when the gas become ionized, the electric field created by the potential difference between the anode and the cathode causes the electrons of each pair to move to the anode while the positively charged gas item is drawn to the cathode. Okay, now this you can say the movement of electrons to move to anode and the positively charged ions to anode. This results in an electric signal that is amplified, quoted to exposure and displayed as a value. Now audible alarm rate meters. Okay, now what they do? Audible alarms are devices that emit a short beep or chip when a predetermined exposure has been received. You can see in the diagram how it looks, audible alarm rate meters. Now, it is required that these electron devices are worn by the individual working with gamma emitters. Okay. Now, these devices reduce the likelihood of accidental exposure in industrial radiography by alerting the radiographer to exposure levels or dosages of radiation above a present value, or you can say above a preset value. Okay. So it will, you can say, alert the radiographer. Okay, if it is exposed to a certain radiation above a preset value, above a preset amount, you can say. Now, it is important to note that the audible alarms are not intended to be and should not be used as a replacement for survey meters. So, modern survey meters have this alarm feature already built in. Now, we have advanced survey meters with us, which have the audible alarm rate meters also. Now, pocket dosimeters. See, these are used to provide the wearer with an immediate reading of his or her exposure to X-rays or gamma rays. So they are commonly worn in the pocket. The principal advantage of this pocket dosimeter is its ability to provide the wearer an immediate reading of his or own radiation exposure. It has also an advantage of being reusable. So the limited range, inability to provide a permanent record, and the potential for discharging and reading loss due to dropping or bumping are a few of the main disadvantages of a pocket dosimeter. Okay, now there are two the types of commonly used like of in the industrial radiography are direct red pocket dosimeter and the digital electronic dosimeter. Okay, these are used to provide the wearer an immediate reading of his or her exposure to X-rays or gamma rays. Now, direct read pocket dosimeters. See, a direct read pocket dosimeter is generally of the size and shape of the fountain pen. The accumulated dose value can be read by pointing the instrument by a light source or observing the internal fiber through a system of built-in lenses. You can see in the diagram how the direct read pocket dosimeter looks like. Okay, the fiber is viewed as a on a translucent scale. You see the scale, which is graduated in pockets in units of exposure. The typical industrial radiography pocket dosimeters have a full scale reading of 200 mR, but there are designs that will record higher amounts. So during the shift, the dosimeter reading should be checked frequently and exposure should be recorded at the end of each shift. Now you have digital record dosimeters. Okay, these dosimeters they measure both. You can see in the diagram on the right hand side how it looks. These dosimeters measures both dose information and dose rate and display them in digital form. Okay, these also include an audible alarm feature which emits an audible signal or chirp with each recorded increment of exposure. So the frequency of the chirp rate of the alarm is proportional to the radiation intensity. Some models can also be set to provide a continuous audible signals when the preset exposure has been reached. So this is about digital electronic dosimeter. Now film badges. Now personal dosimetry film badges are commonly used to measure and record radiation exposure due to gamma rays, X-rays or beta particles. So detector, as the name says, a piece of radiation sensitive film. The film is packaged in a light-proof, vapor-proof envelope preventing light, moisture or chemical vapors from affecting the film. The film badges need to be worn correctly. The film badges need to be worn correctly so that the dose they receive accurately represents the dose the wearer receives. So whole body badges are worn on the body between the neck and the waist, often on a belt or a pocket shirt. This is a kind of a film badge. The film is contained inside a film holder or a badge. The badge incorporates a series of filters to determine the quality of the radiation. You can see the series of filters in the diagram. Okay, it is shown here. The radiation given of a given energy is attributed to a different extent by various types of absorbers. Therefore, the same quantity of radiation incident on the batch will produce a different degree of darkening under each filter. You can see the darkening. By comparing these results, you can see in the diagram different kinds of filters. By comparing these results, the energy of the radiation can be determined and the dose can be calculated knowing the film response for that energy. The badge holder also contains an open window to determine radiation exposure due to beta particles, since beta particles are shielded by a thin amount of material. The major advantage of this film badge is as a personal monitoring device are that it provides a permanent record. It is able to distinguish between different energies of photons. It can measure doses due to different types of radiation. The major disadvantages are that it must be developed and read by a professor or by a processor, which is time consuming, and prolonged heat exposure can affect the film. Now, thermoluminescent dosimeter, TLD. Now, these are often used instead of a film badge. Like a film badge, it is worn for a period of time, for usually 3 months or less, and then must be processed to determine the dose received. Now, TLDs can measure doses as low as 1 mR and they have a precision of approximately 15% for low doses, which improves to approximately 3% for higher doses. TLDs are reusable, which is an advantage over film badge. However, no permanent record or readability is provided, and an immediate on-the-job readout is not possible. So this is another kind of a dosimeter called as thermoluminescent dosimeter (TLD). You can name it. A TLD has a phosphorus has a phosphor such as lithium fluoride (LiF) or calcium fluoride in a solid crystal structure. When a TLD it is exposed to ionizing radiation at ambient temperature, the radiation interacts with the phosphor crystal, causing some of the atoms in the material to produce free electrons and become ionized. The free electrons are trapped and locked into the place in the imperfections in the crystal lattice structure. So heating the crystal causes the crystal lattice to vibrate, releasing the trapped electrons in the process. Now released electrons, these return to the original ground state, releasing the captured energy from ionization as light. Hence the name thermoluminescent. Instead of reading the optical density of a film as it is done with the film badges, the amount of light released versus the light of an individual pieces of the thermoluminescent material is measured. The glow curve produced by this process is then related to the radiation exposure. The process can be repeated many times. So now the safety control. The safety controls are also important as a, so you can say, for in radiography. Now, since X-ray and gamma radiations are not detected by human senses, and the resulting damage to the human to the body is not immediately apparent, a variety of safety controls are used to limit exposure. The two basic types of radiation safety control used to provide a safe working environment are engineered and administrative controls. Now, engineered controls include shielding, interlocks, alarms, warning signals, and material containment. Administrative controls include posting, procedures, dosimetry, and training. So, engineered controls such as shielding and door locks are used to contain the radiation in a cabinet or a radiation vault. You can see how it is shown in the figure. Now, fixed shielding materials are commonly, you can say, high density concrete or lead that are used. And that we have discussed in previously also that what kind of shielding materials are used in radiography. So, lead and concrete are the two most common materials that are used as a shielding material. Now, door interlocks are used to immediately cut the power to the X-ray generating equipment if a door is accidentally opened when X-rays are being produced. See how they have tried to control the X-ray. You can say, so that it doesn't cause any damage. It doesn't cause any damage. So warning lights are there. So warning lights are used to alert workers and the public that the radiation is being used. So this is also good. Now sensors and warning alarms are often used to signal that a predetermined amount of radiation is present. Safety control should never be tampered with or bypassed. So we should be aware of the safety control. Like this is the kind of engineered control. Okay, so like the using of shielding controls, using of door and locks, using of warning lights, using of sensors and warning alarm. These are all engineered controls for safety of the worker. When a portable radiography is performed, most often it is not practical to place alarms or warning lights in the exposed area. So ropes or and signs are used to block the entrance of to radiation areas. This is the line of a signal or you can say sign that is shown on the right hand side in the figure and to alert the public to the presence of radiation. This is also good activity. Occasionally, radiographers will use battery operated flashing lights to alert the public to the presence of radiation. Okay, this is also night. Say that they somewhere they use battery operated flashing lights also to alert the public. Now, safety regulations classify the areas surrounding the location where ionizing radiation is present into restricted areas and controlled areas according to radiation intensity level. Restricted areas with dose rate higher than 300 mR per hour must be secure so that nobody can enter this area. If anybody accidentally enters this area, radiation must be terminated and the person must be checked. Okay. The access is only permitted under specific conditions, and if there is an absolute need for it, the body dose should be calculated and the personal dose measured. Now, the control areas, there are areas with door rates which are equivalent or to higher than 0.75 mm. So, control area must be cordoned off and provided with a radiation warning signs. Okay, now we'll go start with the MCQs. See, we have studied today a lot about radiographic interpretations in like for weldings or for castings. Okay, in this we have seen various diagrams also, which were able to let us understand and interpret very easily that how the defects or discontinuities will look like. And we also studied about various detectors that are being used by the people working in radiographic industry or the radiographers and how these different detectors or safety devices are used and are or you can say are helping them to stay away from radiation or to find out the exposure. So these all instruments are advanced instruments and one should know about a radiographer or a person working in the radiographic field should be aware of those instruments. Okay. Secondly, there are some safety controls shown. Some are, you can say, so these safety controls should also be known and well understood by the people. The most common thing you can see the signal that have been shown. You're saying that caution sign with it. So if anybody sees such kind of caution sign in the nearby or you can say area, you can one should be aware that there is some kind of a testing going on. So one should not disturb that area or try to enter that area reading, because it may lead to some you can say unwanted effects. So now the MCQ. In radiography testing of castings, these are non-metallic oxides which appear on the radiograph as irregular dark blotches. These come from disintegrated portions of mold or core walls or from oxides formed in the melt, which have been not skimmed off prior to the introduction of metal into the mold gas. What do we call this? Either blows or gas porosity or shrinkage or sand inclusion and loss. I told you when we were studying this kind of defect, it is called as a sand inclusion and loss. Now, in radiographic testing of castings, it is usually occurs at a time when the melt has almost reached solidification temperature and there is no source of supplementary liquid to fill possible cavities. Okay, so what do we call this? A cavity shrinkage or a dentic shrinkage or a filamentary shrinkage or a commuted tomography. See, we have to be understood that what do we call this? So what do we call this? We call this as a cavity shrinkage. Now, in radiographic testing of casting, it is a distribution of very fine lines or small elongated cavities that may vary in density and are usually unconnected. Okay, these are unconnected. So it comes to dendritic shrinkage. Okay, distribution of very fine lines or small elongated cavities that vary in density and are usually unconnected. Dendritic shrinkage it is called. Okay. Now in the radiographic testing of castings, it usually occurs as a continuous structure of unconnected lines or branches of variable length, width, and density, or occasionally as a network. So what do we call this? What do we call this? We call it as a filamentary shrinkage. Okay. Now in radiographic interpretation of for welds, it occurs when the weld metal fails to penetrate the joint. It is one of the most objectionable weld discontinuities. Now weld discontinuities. The appearance of a radiograph in a dark area with well-defined straight edges that follows the land our foot face down the center of the weldment. What do we call this? We call this as the incomplete penetration. Okay. Now in radiographic testing of casting, it is a powerful non-destructive evaluation NDE technique for producing 2D, 3D cross-sectional images of an object from flat X-ray images. Characteristics of the internal structure of an object such as dimension, shape, internal defects, density and density are readily available from images. So what do we call this? I've shown you an image in which there was a turnable table and there was a you can say source and X-ray, which is called as a computed tomography. Okay, called as a computed tomography. In radiographic interpretation for weld, it is a condition where the weld filler metal does not properly fuse with the base metal or the previously weld cast metal. The arc does not melt the base metal sufficiently and causes the slag molten puddle to flow into the base material without bonding. What do we call it? We call it a cold lap. Cold lap. Now, in radiographic interpretation for welds, it is the result of gas entrapment in the solidifying metal. It can take many shapes on a radiograph, but often appears as dark round or irregular spots or specks appearing singularly in clustered orange zones. What do we call this? We call this as a porosity. Okay, the trapped gases. When the word trapped gases come, porosity, you can think of that. In radiographic interpretation for the well, it is caused when flux-coated electrodes are contaminated and with moisture. The moisture turns into a gas when heated and becomes trapped in the well during the welding process. What do we call it? We call it as cluster porosity. I've shown this in the diagram also. Yeah, I've shown you this in the diagram also, not the cluster porosity. Now, in radiographic interpretation for welds, Apart from crystal photography, now we are going ahead. In radiographic interpretation for welds, these are non-metallic solid material entrapped in the weld metal or between weld and base metal. In a radiograph, dark, jagged, asymmetrical shapes within the weld or along the weld joint areas are indicative of it. What do we call this? Are indicative of it. What do we call this? Slag inclusion. So we have studied about all the defects. We studied about all the, you can say, defects for welds and castings that the radiographic can help you to detect. We have studied about all the detectors, all the types of detectors. We have studied about all the safety control in radiography. So for now, you can go and refer these books if you want, and these books may give you also advanced knowledge in these topics with more diagrams, if possible. And if you read these books, it will automatically increase your knowledge. So it is for your own benefit. So you can read books if possible and increase your knowledge in this field. And so reading is a very good habit. Thank you all.